Today we will learn about a mind-blowing concept known as Fourier transform, which has completely revolutionized the way we study and apply ideas in physics and engineering. You might have heard that a number line is a straight line which we use to represent all real numbers. It usually has 0 marked in the center, with positive numbers placed on the right and negative numbers on the left. Now, when we introduce something known as imaginary numbers, things move beyond this one-dimensional line. An imaginary number is formed by multiplying a real number by I, where I squared equals -1, and we know that there exists no real number whose square can be a negative number. So, this I is an imaginary number. Because of this, imaginary numbers cannot be placed on the same real number line. So, we extend our idea into 2 dimensions, called the complex plane. In this plane, the horizontal axis, or the x-axis, represents the real part, and the vertical axis, or the y-axis, represents the imaginary part. A complex number is written as a plus ib, where both a and b are real numbers. Now, this complex number can be represented as the point A and B on this complex plane, where A is the real component and B is called the imaginary component. This way, every complex number has a natural geometric position on the 2D plane. Now, in this complex plane, imagine drawing a circle centered at the origin with radius r. Any point on this circle can be described using the angle theta it makes with the positive real axis. Using basic trigonometry, we can show that the horizontal distance from the origin is given by r times cos theta, and the vertical distance is given by r times sine theta. So, this point can be written as r cos theta plus I r sine theta, right? Then came a genius mathematician named Euler, who discovered an extraordinary connection between exponential and trigonometric functions, and he showed that a constant number e raised to the power of I theta is exactly equal to cos theta plus I sine theta. If you want to know how he obtained this relationship, I have made a video on the same, and the link is in the description. Thus, r times e raised to the power of I theta becomes this. So far, so good. Now, if we rotate this point around the circle with a constant angular speed omega, the angle theta keeps increasing steadily over time. Angular speed omega simply means how many radians the point sweeps per second. So, as the point moves, theta becomes equal to omega times t, where t is the time. Thus, the equation of the rotating point becomes r times e raised to the power I omega t equals this. Before we move further, let us finally learn a few simple terms, which might be introduced further into the explanation. The time period t is called the time taken to rotate one complete cycle or one full turn. So, t is how many seconds per cycle. Then the frequency f is how many such cycles happen every second, which we also call hertz. These two are reciprocals of each other, so the time period t is 1 divided by the frequency f. For example, if f is 1 cycle per second, then t is 1 second, and if f is 2 cycle per second, then the time period t is half seconds. Now let us see how angular speed omega fits in. Angular speed omega tells you how many radians the rotating point covers each second. One full rotation is 2 times pi radians, and the time to complete it is t, right? So omega times t is 2 pi. Now t is 1 over f, so this means omega is 2 pi multiplied by f. This means omega is a direct representation of the frequency as it is directly proportional to f. Keep this in mind. So what we make out till now is that if I plot the horizontal distance r cos omega t with respect to time, we get this cosine graph where r just acts as the amplitude of cos omega t, and then plotting this vertical distance r sine omega t with respect to time, we get this sine graph, and together, their combined motion is simply a circular motion. Now we will do something interesting. Consider only the vertical motion or sine omega t for now. Take 3 such graphs having different frequencies and amplitudes. Omega with amplitude r, 1, then 2 omega with amplitude r, 2, which means this one has twice the frequency, as compared to the first one, and 3 omega, or thrice the frequency, as compared to the first one with amplitude r, 3. Then simply add them together, and you will get this amazing graph. Look at how this graph is just the combined motion of the y component of these 3 circular motions. This is what a signal looks like in real life. Most real-world signals, like a musical note, a person's voice, or even an electrical vibration, are made up of many waves of different frequencies and amplitudes all added together. But sometimes, instead of just looking at this messy combined signal, we want to know what individual waves were used to make this original signal, which means what all frequencies are present in this signal and how strong each one is. This is exactly where the Fourier transform comes in. It is a mathematical tool that helps us separate a complex signal into its basic frequency components. Think of it as using a magical prism, but instead of splitting white light into colors, it splits a signal into its different frequency components. For that, we start with a signal that varies with time. This signal is our input, usually written as f of t, where t represents time. The Fourier transform takes this time-based signal and analyzes it to find what frequencies are hidden inside it. After applying the Fourier transform, what we get as the output is another function, usually written as f of omega, where omega represents angular frequency. This new function tells us how much of each frequency is present in the original signal. We get a graph somewhat like this. The height or magnitude of this output curve gives the amplitude of each frequency. So, in simple words, the Fourier transform takes us from the time domain, where we see how the signal changes over time, to the frequency domain, where we see what frequencies make up that signal. And the mathematical tool that helps us do the same is none other than this integration. Let us break it down step by step. Okay, just note that the engineers have the habit of using j instead of I for denoting imaginary number. So we can write this e raised to minus j omega t like this. Thus, this f of t times e raised to minus j omega t will become this complex number, right? So, if we want a point using this in the complex plane, then we will write it like this. Now let us do some fun with this. Consider this f of t is just 1. Now, fix a value of omega and rotate this point. So what we get is simply a circular path like this, right? Even if we change the value of omega, we still get this curve. Note how this curve is fully symmetric around the origin. So if we kind of consider its center of mass, we see that it stays exactly at the origin. The contributions from all points around the circle perfectly cancel out in every direction. This symmetry shows that when the signal frequency does not match the rotation frequency omega, the net contribution is 0, which is why no peak appears in the Fourier transform at any frequency. Now, as soon as we change this f of t to sine of capital omega times t, where capital omega denotes the signal frequency, which we will keep 5 for this case, and fix our rotation frequency, or small omega, at 1 for now, and then rotate this point, which will be written like this, we see a beautiful flower-like shape. Now, do one thing. Slowly, we will try to change the value of our rotation frequency, or small omega, and observe what happens. We see these beautiful patterns emerging just by changing this small omega. But hey, again, notice that as long as the rotation frequency, small omega, does not equal the signal frequency, capital omega, the curve remains symmetric around the origin. Once the small omega finally matches capital Omega, the symmetry breaks, and all the contributions align in one direction, producing a strong net amplitude. And that is exactly what the Fourier transform captures. It tells us which frequencies are in sync with the signal and shows them as peaks in the frequency domain. So, in order to get this peak, we use this idea of integration. We essentially add up all the tiny contributions of the rotating point over time, like summing up many little arrows along the circle. When the rotation frequency matches the signal frequency, these contributions all point in the same direction, so they add up to a large value, creating a clear peak in the Fourier transform. If the frequencies don't match, the contributions cancel out in different directions, giving little or no net amplitude. Now, let us do some more fun. Consider this: f of t is 2 sine of capital omega 1 t plus 3 sine of capital omega 2 t, where capital omega 1 is 5 and capital omega 2 is 7. Also keep small omega as 1 initially. We get this shape, which you can see has its center of mass at the origin. Now, as we keep increasing small omega, notice how the curve is still having the center of mass at origin, except for the case when my small omega equals capital omega 1 or 5 and capital omega 2 or 7, where the mass is distributed downward. Also notice that if I change the amplitude when small omega equals capital omega 1 to 1 instead of 2, the curve shifts upward, denoting that the strength or amplitude of the corresponding frequency decreases. This shows how the Fourier transform not only identifies the frequency present in the signal, but also directly reflects its amplitude, giving a complete picture of the signal's composition. Actually, when we compute these integrals, they give us something called the Dirac delta function, which is like a spike at a single point, and it is defined as 0 everywhere except at one exact value, and yet its total area is 1. This is perfect for our case because it picks out exactly the frequency where the signal and rotation frequencies match each other and ignores all other frequencies. Thus, using the Dirac delta, the Fourier transform directly shows a sharp peak at the frequency present in the signal, and 0 elsewhere. If you enjoyed this video, please don't forget to like, share, and subscribe to our channel. Also, you can support my channel by joining our community and becoming a member. So good!